Hey robot makers, hope you're having a good day so far. So do you want to understand how to use addressable RGB LED strips in your robot projects and learn how to program them with the Plasma 2040? Then this is the show for you. That was a bit of a mouthful. So let's dive straight in. My name's Kevin. Come with me as we build robots, bring them to life with code and have a whole load of fun along the way. Okay, let's get over to our keynote and look at today's show. So yes, it's all about LED RGB strips today. So the session goals for today is we're going to be looking what's inside an RGB LED. We're going to have a look at some colour theory as well, because we'll need to understand that to be able to use these properly. We're going to have a look at the different types of RGB LED strips, because there are quite a few. We're going to look at things about the pitch, the anatomy of the RGB LEDs, how they actually work, and what is the Plasma 2040 and how can we use that in our projects. So let's get straight into this. So what is an addressable RGB LED? So this little white thing that we can see on the right hand side here, Adafruit calls these neopixels, but it's an RGB LED. So RGB stands for red, green, blue. LED is light emitting diode. So it's actually three light emitting diodes that can shine their colours and we can control them using code. And what we get is an LED that we can change the colour of. Now some of these actually have four lights in them. They have a white one as well. So you might see these in the sort of higher end LED strips. So instead of just merging the three colours together, they have an extra one for white. So you get a really brilliant pure white. So yep, inside there is an integrated circuit. That's in the diagram there. That's this tiny little black area here and all the little wires and everything that connect it together, tiny little whisker like wires. Then we have the LEDs themselves. So on this one there's the green one there, the red one in the middle, and then the blue one on the right hand side, and optionally they have a white one. I'm not sure that would fit in there, but they do have that as well. And they have a controller chip. So this controller chip in this example is the WS2812, and we'll see this one quite a lot. I think it's actually mentioned in the Raspberry Pi Pico handbook as well. So we're going to have a quick look at some colour theory today, just to understand how all this actually works. So you can make any colour by mixing red, green and blue lights together, and varying the brightness of them you can create a whole rainbow of colours. So if we look at the three primary colours that we have here, we've got red, we've got green, we've got blue. And if we mix red and green together, and on our little chart here we can have a look, if we get red and green together, we get yellow. And you can see on the little diagram there, we've also got yellow in the middle. If we mix green and blue together, we get cyan. This reminds me of my ZX Spectrum days when we used to have that as a colour option. I always thought it's an odd choice of word for colour, because I thought it was just like a light blue, but no, cyan is the colour. And if we mix red with blue, we get magenta. Again, I would have thought that was more of a purple, but magenta is the correct term for that. And if we mix all three together, we get white, we get pure white. So you can see there, if we turn off our different RGBs, we get black. If we turn on the red only, we get red, and so on. So a little truth table there on mixing those colours together. So we can express these colours as a colour wheel. You often see this in graphic design. So this is all the different colours, all the different saturations of them colours as well, all the way through to white from their full strength of colour. And with these colours, we can have what they call complementary colours, we can have monochromatic colours, we can have analogous colours, triadic colours, and tetradic colours. So we're going to have a look at what they are all about as well. So complementary colours are on opposite sides of our colour wheel. So in this example here, we've got red and we have cyan. So they are complementary colours. They're on opposite sides and they provide the highest contrast, which is the highest impacting colour combination we can have. And it can be anywhere on that colour wheel. Graphic designers often use this to make two colours really stand out against each other. So they appear to be brighter and more prominent if you use these two colour combinations. So monochromatic colours is where we have a number of shades or tones or tints based on one particular colour. So this provides a subtle and conservative colour combination. It's a very versatile colour combination, easy to apply to design projects for a harmonious look. So this is really just about picking one colour and adjusting the saturation of the colour. And you can have as many different bands of that as you like actually. So analogous colours sit side by side. So in this one we've got three colours that are set side by side on the colour wheel. This colour combination is very versatile, but it can be overwhelming from a design perspective. So if you're designing a web page and you've got too many of these, it can kind of muddy the message that you're trying to convey within colour. So the colour balance, to balance the analogous colour scheme, we usually choose one dominant colour and have the other ones as accents to that. So we just have one strong colour, maybe a really solid background, and we just have some lighter variants of that as well, using the analogous colour scheme. Then we also have triadic colours. This sounds like really, I don't know, an odd word, triadic colours. So these are 3 evenly spaced colours around the colour wheel. And again, it can be any combination, any one colour, and then you'll get the other 2 side by side. So they provide a high contrast colour scheme, but less so than the complementary colour combination, making it a bit more versatile. And you definitely see this on many brand designs. They'll pick a strong colour there as their main brand colour, and then they'll have triadic versions of that just to complement it and make things look sort of, you know, what's the word, enhanced and together. So this combination creates bold, vibrant colour palettes. Next we have, I thought this was like tetratic, I'll try that again, tetratic colour schemes. So these are actually 4, I've said 3 there, in my rush to get these notes out. 4 colours that are evenly spaced on the colour wheel. So tetratic colour schemes are bold and they work best with one colour to be dominant, and then the other ones as an accent to this. Again, you'll see this on web design, product design, anywhere where colour schemes are used, you'll get one solid colour and then you'll have other ones as variants of that as well. So the more colours you have in the palette, the more difficult it is to balance. So companies usually pick 3 or 4 main colours, and then they might have the complementary colours to that. They might have some gradients that they use on some of the literature as well. So this is all part of the colour theory and design theory that we're going to use today. So warm and cool colours. So again, I've not updated my notes here. I thought I'd been through these. No. So the colour wheel can be divided into warm and cool colours. And you'll see this on a lot of the remote controls that you have for... I'm just trying to think if I've got one actually. If you have some LEDs and you have a remote control for them... No, I don't think I've got one to hand. They'll often sort of have like warm colours, cool colours, and really they're just looking at different halves of the colour wheel there. So you can see warm colours, as you'd expect, are the sort of yellows and reds. The cool colours are more of the blues and some of the greens there. So the warmth or coolness of the colour is also known as the colour temperature. So when I'm setting up my studio, for example, if I've got quite flush skin, I might decide to dial down the colour contrast, the colour temperature, so that there's a slightly more green, so I don't look quite as red, for example. You can see that my reds are quite vibrant. So I can set the lights using the colour temperature, and cameras work in the same way as well. When you might see cameras talk about white balance, and that's to do with the colour temperature, usually expressed in Kelvin. So you might have like 4,500 Kelvin as your colour white balance, and that's what I've got my camera set to at the moment, for example. It's about 4,700, I think it is. So the colour combinations found on a colour wheel often balance of warm and cool colours. According to colour psychology, different colour temperatures evoke different feelings, different emotions. So for example, warm colours are said to bring a coziness and an energy, and cool white colours are associated with serenity and isolation. So really quite interesting topic to delve into, and there's quite a lot of resources that are available for free on the web to do with colour palettes and colour schemes and so on. So the last bit of colour theory we'll look at, and this is relevant to what we're going to be doing because we actually can change the value based on this. So there are different colour spaces. So we've looked at red, green and blue before, where we can mix all those different colours together and get white or various different colours. But you can change the colour in a different way and look at it from a different perspective. And this is quite similar to how old-fashioned TVs worked when they had, before we went digital and everything was analogue TV. We used to use hue, saturation and luminance. And we'd have 3 different signals which would combine behind the CRT to create these different colours. And you could adjust the hue, and that would often look like, if you was adjusting the hue, it might go more pink or it might go more green, and that was just adjusting it ever so slightly on this hue scale. But with hue, you can represent every single colour of the rainbow just by adjusting the hue value, and in our example from 0 to 1. So if you imagine the colour wheel, we're kind of going round the outside of the wheel, so the very top is 0, and by the time we got back to the very top again, that's 1, and every value in between. And we'll have a look at how we can represent that in a second. Saturation is how much of that colour that we're actually using. So if we have no value at all, then it would be black. If we had half the saturation, it would be half whatever the colour is. So red, it would be sort of a dark red. And then if we had 1 as our saturation, we've got full saturation, it'd be the full redness that our monitor, our screen, our RGBs can provide. And then luminance is it's almost the opposite of saturation in that this is an expression of brightness. So how bright do we want our pixel to be? So when we're working with RGB LEDs, it's how much energy, how bright the LEDs are. So sometimes this is written as HSV, with the V standing for value, so hue, saturation and value. Sometimes it's written as HSL, which is luminance, the L stands for luminance, or HSB with the B standing for brightness. So they're all meaning the same things, but it's a slightly different colour space than RGB. With RGB, we typically work between values of 0 and 255, and we save that as 1 byte, whereas with hue, saturation and luminance, we work in values between 0 and 1, which can seem a bit counterintuitive if you've not worked in that area before. So like I said, we can think about hue being the outside rim of our colour wheel, going from the very top at 0 all the way around back up to 1, and every colour represented along the way on that path. Saturation is how solid the colour is, and luminance is the brightness. So let's have a look at some LED strips. There are quite a lot of different LED strips, so we're going to focus on some of the common ones that we can get. So they commonly come in either 3 or 4 wire. So I've got a couple on my desk here. I've got one here which is actually the one that's going round my room. So if you look, there's an LED strip going all the way around the room there in red. And I can program that from my phone just using the Philips Hue app. And this is a little offcut. I didn't quite need it because all the way around the room, and this was a little piece that I didn't need. And I knew that I could actually use this. I can plug this into our Plasma 2040 today, and we can actually get these LEDs to light up if we wanted to. But if I just hold this in front of the camera, in fact, if we go to the overhead one for a second, and let's put our overhead light on. Let's see if we can get this into focus. So you can see there, if I just hold it like so, that there is a little LED, just trying to get it in focus there, put my hand behind it, there we go. So you can see there we've got a little connector, 12 volts, green, red and blue, and every now and again there's another bit where we can cut the strip, and there seems to be about 3 LEDs on this one per section. That's how they've decided to manufacture these. So that one has red, green and blue, so it doesn't have the white LED in there, it's just got the 3, and that one is probably the because it's got 4 connectors on it, it's probably the 4 wire variant, the APA102. So like I said, there are lots of variants of this. You might say, well, what about the WS2801 or the WS2811B? There's lots of different variants of this, and that can get really, really confusing. Sandy's talking about printers using cyan, magenta, yellow, and K, which is black. Never understood why they don't call it CMYB. I'm not sure either. I think B might get confused with blue, so they've decided K for black. And that's because it's printing, because it's colour. It's very different when you're painting, mixing colours together. If you mix like green and red, do you get brown or something if you mix with the paints? I can't remember now, but it's very different than mixing with colour, with light. Okay, so that's the different variants we've got there. So RGB is red, green and blue. You sometimes see RGBW, which is the red, green, blue and pure white. So in my kitchen I've got some LED strips underneath the counter, under the worktop, and they have a special LED just for pure white. It's like a really, really bright light. And yes, the WS2812 is very, very common. You'll see that in a lot of LED strips that you can purchase. And the APA102 is the one that I'm actually using today. So that's what we're going to be focusing on. But WS2812, APA102 are the most common ones. So the next thing is about pitch. So this isn't about pitch. You can hear this is about spacing between 2 LEDs. So on this particular top one, we have a 28mm pitch, meaning that the space between each RGB LED is 28mm. Now, when you're buying these, they actually express this as how many LEDs there are per meter, because you tend to buy it on a roll, and how many meters per, how many meters do you need for your particular project. So this one is 30 meters per roll, so they're really quite widely spaced. And then on the bottom row there, we've got a 12mm pitch, so there's 12mm between the middle of each of those RGB LEDs. and therefore it's 60 LEDs per meter, so a lot denser. And the ones I've got on the desk are even tighter than that, so they have a really if I hold this up and show you, you can see there the LEDs are really close together, so that's got a really high number of pixels per meter. Okay, so let's have a look at the anatomy of an RGB LED. So as we said at the beginning, there is this white neopixel, this white sort of box that has the RGB LEDs within them and the driver chip as well. And then on the very edges of the strip, there is some connectors. And when you buy them on a roll like this, all the connectors are already connected together. So you can see on this one I've got just here, there's a little pair of scissors there, sort of suggesting that you can cut that along that point, and then it's very easy to connect them back up because they've got those solder pads ready for you to solder extra wires on, or you can buy little connectors that clip onto the edge there. But you can, in theory, cut it at any point if the wires were exposed, but they're probably not exposed until they get to that very end bit where there's the cut point. So looking top to bottom, we've got ground, we have clock in, we have data in, and we have 5 volts in. The RGB LED will consume that, but then it passes along to the next one in the chain, the same ground, the same clock out, data out, which it may have changed, and we'll talk about that in a second, and 5 volts. So that's for the 4-wire variety. The 3-wire variety just has the data, it doesn't have a clock. And the clock is used to keep everything in synchronization. It's a really common way of keeping things that need to be synchronized and passing things along with a data package by having a sort of metronome or clock. And each time the clock ticks, you know, you can move your data package along to the next RGB LED and so on. So you can see there, it's going to pass it along to the next one that's next along in chain. So how addressable RGBs work? So it's about passing the baton. Now this is the thing I didn't understand until I started playing with them. I thought, how on earth do you have a long strip of LEDs and you can cut them at any point, you can add to them at any point, so how does it know how many there are? Well, we do this in code. So the way that the RGB LEDs work is that they just know that they've got a neighbor next to them, and they're going to take some data, they're going to take their data off the stack, and they're going to pass it along to the next one. So the number of LEDs that we have in a strip, we need to define that in our code, and then we can pass the whole block of data, which is in a specific low-level format. We don't need to worry about that. The code takes care of that for us, the libraries. So we have an array of RGB values. We construct that for each LED in our strip, and then we pass that block of data to our driver, and that will basically decide how it passes it along to each data channel using the clock to make sure that everything is in sync. So the first module that we have in our strip is 0. So that's the index that we're going to use. We're going to have the first one is 0. It's going to read the data that comes along from the driver. It's going to say, right, so I've got red as full strength, so it's got a 1 value. I've got a green as 0, and I've got a blue of 0. So I'm going to set both of them to off and the red LED to on. It then takes that data off that little stack of data and passes it over to the next one. So the next one in the chain is RGB1. So that's going to do the same thing. It's going to read the data, it's going to set its RGB LEDs. It's then going to pass the rest of the data minus its data along to RGB LED number 2, and so on all the way along until we get to the very last RGB LED. So if we don't define the right number, and we can play with this in a second on this strip just to see what happens if we don't define enough in our array, or if we define too many and so on. So that's how it works. It's quite clever. We just have this big block of data and everybody just takes the thing off the top. It's a bit like having a stack of pizza boxes and somebody just takes the top one off and then the next person takes the next one off and so on. So you just have to understand in advance the order that you need them. So the very last one that you have on the stack needs to be the very last RGB LED pixel. It's always about pizza. So what is the Pimoroni Plasma 2040? So it's a Raspberry Pi 2040 powered RGB LED controller. So Pimoroni have created a Plasma 2040 that works with the WS2812 or NeoPixel and the APA 102 or Dot Star addressable LED strips. So the most common ones. It has a USB connector for programming, so it makes it really easy to connect into your computer. It's got some screw terminals you can see on the right hand side there to connect our 5 volts, our data, clock and ground. If we're only using the 3-strip version that doesn't have the clock, we just don't plug the clock terminal in, it works just as well. And then we have 2 programmable buttons, you can see A and B there, and we also have one onboard RGB LED NeoPixel, as they're called. That was a really smart move by Adafruit as well to copyright the term NeoPixel in all their products, because you can copy their code, you could recreate their boards if you knew how to do that, but you can't call it a NeoPixel because they own that. That's their terminology. So, Plasma 2040 features. So this has 2 megs of onboard flash for storing our programs, which is loads of storage for the kind of files that we're going to be storing on here. We're not going to be creating anything really clever with this from a data point of view. We just write little algorithms that make the LEDs go into various different patterns. So it's compatible with 5 volt WS281 NeoPixels. It's also compatible with the SK6812 as well. I told you there's loads of variants of these. And the APA 102 dot star or SK9822 LEDs. So if you're buying them, it usually tells you what they are. But think about it's 5 volts. That strip that I just dropped on the floor, which is the one that goes around my room, that's actually 12 volts. So when I plug that in, the LEDs barely glow. There's not enough juice in them to actually power them up. It also has the USB-C connector, which we can use for programming and power. Can drive an LED strip up to 3 amps, so it's actually quite a lot of power. They do get quite warm as well, these RGB LEDs. I was quite surprised at that. So they're definitely pulling quite a bit of power there, but not enough that it's actually tripping the board. And the board has some really clever low current sensing and overpowerage sensing as well, so it'll definitely detect if you're drawing too much power there. It has the Quest connector, which is the quick/stemma QT connector. So if you want to connect any I2C devices with that kind of connector on, you can easily do that too. And it's fully assembled. There's no soldering required at all. Everything just screws together using those screw terminals or plugs in with the connectors. So very, very simple. And it's tiny as well. I mean, you can see on the overhead screen here. So it's 58 by 28 by 12. So it's very, very small. Very easy to fit in a project. I mean, these things are quite big. The connectors are quite chunky as well. And you get the connector and the wire with it as well. And there's one at the end if you want to connect even more things to the chain. There's also some spare wires as well if you want to add additional power to your project, because you've got like absolutely miles of this stuff. You can power it externally as well. Okay, so if you like my content, you want to help me out, you can do that in a really easy way, which is free. You can like this particular video, you can give me a comment, tell me if you've ever played with the LED RGB strips as well, and also just hit that little bell if you want to get notified next time I go live. And I do go live every single Sunday at 7 PM local time to me in the UK, which is either GMT or BST, British Summer Time. So we're in British Summer Time at the moment, but when you're watching this back, you might not be, you might wonder why have you missed the show. But I always give a notification out when I'm going live, but it's on the Sunday, 7 o'clock. Okay, so there is a software library as well that goes along with this Plasma 2040. Really, really good quality code in here. So we have C++ library, we've got MicroPython library, and there's also a CircuitPython library as well. So Pimoroni have created some software libraries to make coding this ridiculously easy. So we're going to go through that in the demo in a second. And the Plasma 2040 is firmware agnostic, so it doesn't really care what you use. You can use CircuitPython, the official MicroPython, or Pimoroni's batteries included MicroPython that works with all their products, and C++ if you want to do that too. Okay, so MicroPython code. Let's have a look at 2 examples. So we're going to look at the APA 102 example code. So this is some code I've just thrown together very quickly. So the first thing we do is import Plasma, which is the Plasma library. So we'll have to have just downloaded that first. From Plasma, we then import Plasma 2040, which is like a sub-library within that library. And we're also importing time and sleep. I don't think we use it in this example, but I use it quite a lot. We use the sleep function quite a lot with LEDs because we want to, when we're doing rainbows and things, there's usually some kind of animation aspect to it. So we'll use the sleep function to speed up or slow down that. So the next thing we do is we create a variable that's called num_LEDs, which is the number of LEDs that we have in our strip. And this one I've defined as 150. Not sure if it's exactly 150, but I've just put that in and that seems to work fine. It's definitely more than 100. And we have frames per second, so how quick do we want this to work? So I've just put FPS there as well. So the LED strip, we then create a variable called LED strip. We then make it of type plasma.apa102. We then specify the number of LEDs. Not sure the next two variables are for. Maybe Chris or Sandy could help me out on that one. But I know that the next two are to do with the pins that are used to speak to either the data line or the clock line. So plasma2040.dat is the pin in effect for the data out, and the plasma2040.clk is the pin for the clock out, so you can see them there. And then we define the LED strip.start and give it the frames per second that we want this to work at. And then we set an LED. So we're going to do this in a minute. This is really fun to do. So LED.set_RGB. So the first variable is the index. So 0 will be the very first RGB LED in our strip. The next one is the red value, the green value, and then the blue value. So set it to 128. It'll be half the brightness of a red RGB. So the very first one will be just a half value. So next piece of code is for the different type of board. So the first one was the APA102. So the next one, sorry, is the different type of RGB LED driver. So this is for the 3-wire. So very similar kind of code, but then when we come down to the LED strip equals, we've got the different driver name there. So plasma.ws28112 instead of that APA102. And you can see there we don't have the clock the plasma2040.clock. We just have the plasma2040.dat in there. Still set the frames per second, and then we still set the RGB value in exactly the same way. It's just that initial part. If you don't get that right, nothing will appear on your RGB LED strip. Okay, so if you want to join me on Discord and you want to continue the conversation, you can go over to our Discord server. So to get to that, just go to action.smarsfan.com/join-discord, and you can join the party there as well. And we are going to have a look at some code now, I think. Yes, demo time. Right, so let me just get Thonny open, and let me just stop the code that's running at the moment. And let me make sure we're all good to go. Yes, I think we are. Right, so what I'm going to do, I'm going to open up this little workbench here. So I've got my bench cam and I've got some example code, but let's write the code from scratch and see this actually work first. And I might zoom in a little bit as well so we can see what's going on. So what I might do is just uncurl that a little bit so that we can see our very first RGB LED there. Okay, so what we're going to do over here in the so I've just got Thonny open. I've installed the Plasma software. I think no, I've not even had to do that, have I? What I've done is I've flashed the Plasma 2040 with the firmware, the batteries included Pimoroni firmware, which you can get from the website, and that's why I don't need to import any libraries already. They've already done that importing for me and built it into the code. So if you try this and it doesn't work, it's probably because you're not using their version. So the first thing I'm going to do is import Plasma, and then I'm going to say from Plasma import Plasma 2040, and then I'm also I'm not going to import anything else then, so I'm going to say number of LEDs is, I'm going to say 150. Not sure if it's exactly that, but it's thereabouts. And then frames per second, I'm going to say 60, and then I'm going to say LED strip equals Plasma. Let's see if we can do some auto completion on here. .apa. It's really bad auto completion on Thonny. There we go, 102, and then we say num_LEDs, which is that variable we created a second ago. 0, 0. And then we say Plasma 2040.dat and Plasma 2040.clock. Okay, and then we will then do LED strip dot start, and we just pass it that frames per second, which is currently 60. And then the best bit is where we light up an LED. I was so stoked when I did this the first time. So set RGB. So we're going to set the very first one, which is 0. Let's make it red. So we're going to do 25500. So the green and the blue we don't care about, we just want the red one. So let's run this and see if I've got any bugs in my code. I want to run it on the Pico. And if everything, we need to give it a name, so let's call this one test RGB. Okay, we can see we have a little LED that's just lit up there. So if I stop that code and run it again, if I stop it, it'll actually go off. If I run that again, we can see the very first one lights up. So let's try changing the value of the second RGB. So if we mix red with green, what are we going to get? Can you remember from our color wheel? Let's find out. We get green. Is that green? That's more of a yellow color actually. If I turn off my overhead light, we might be able to see a little bit better there. And let's try the next one, which is if I mix all of them together, we should get white, which we do. It looks a bit of a bluish light. Let's then change that one so it's just green and blue. So do we get like a bluish color? Now what I'm also going to do is I'm going to change the value. So instead of 255, let's try 128, which is about half the brightness. Let's see what that looks like. So it's just a little bit dimmer there. And let's try just making it green, like so. And then finally let's make it blue. And there we go. Right. Now if we change that index number to be 1, it will actually change the next one along, like so. And if we have two statements, so if we just copy that and paste that in there, so that the very first one we could have as, I don't know, red, and then the next one can be blue. We have red and blue. And let's add a next line to that. And let's make that one green, like so. Okay, oh, and we need to set that to 2. Let's try running that again. This is what I love about MicroPython, so quick to change and change your code. So that's great, we've got like a little RGB thing going on there, red, blue, green in fact. Let's do something a bit more interesting than that. So we've set our first pixel. We're gonna use a loop this time. So while true, so this is going to run until I hit the stop button. It's going to create a little loop, a for loop. So in range I, from I to number of LEDs, so from 0 to 150, because numLEDs is 150. It's going to set each RGB LED, because we've put I there instead of giving it a number. So each time it goes round, that'll increment. And we're going to say if I is greater than 0, then set whatever the value is. So basically do this for every other one. Set them all to be, it looks like that's going to be off. Let's run this and see what happens. We'll create like a little chasing thing. So what it's doing is it's setting it, and then it's setting the one behind it to 0. So wherever this is, it's always the one behind it that's going to be 0. Let's just zoom out a little bit on there. And let's change that, instead of being 128 to 255, let's give it the full brightness there. There we go. So it looks like a little Catherine wheel or something like that. And again, we can change the value of these. We could have that as that value there. So that's like a different color. So that's the first thing we can do with for loops. So let's try a different example. So in this one, we're going to have a whole load of loops. So let's have a look at this. We're going to have a loop that's called L, and that'll go from range 0 to 255, but it'll count up in steps of 10. We're then going to have a loop within that goes from 0 to 255, also that goes up in steps of 10. And then we're going to have another loop that goes from 100 to 255. And the reason I've chosen 100 is because I don't want the LEDs to go completely off. I want them to go lower in value and then back up in value. So let's see what happens. We're going to then say for iron range the number of LEDs. So basically change all the LEDs that are in our LED strip. We're then going to use the different I, J, K and L for the different values. So what do you think will happen when we run this code? Let's press run and find out. So we get a glowing thing. So what's happening is it's glowing, and we've got a sleep function there, and it's sleeping at whatever speed we've set. So we've set it down to be a really fast value. So if I get rid of one of those ones and then run it again, it'll pulse a bit slower. So it's now pulsing a little bit slower, like so. And we can see there, I've just outputted, if I just move my name out the way there, you can see there we've got a little shell counting up, and we can see it's going to get to 100, 110. It's going to keep counting up until it gets to 255 or higher. And it's also changing the color. That's the other interesting thing it's doing. So it's changing the color value each time it pulses. So yeah, this is a quite interesting little algorithm we've got here. So there we go, it's gone back to red, and that's the value's gone back down to 0 now, but then the next value is going to 10. So that's the next little fancy thing we can do. Let's try another loop. So let's go to test number 3. And what we're going to do on here, so we've got some other things. We've got direction, brightness, saturation, and so on. And now, do I change the saturation on this one? I don't. So what we're going to do on this one, instead of setting the RGB value, we are going to set the hue, saturation, and brightness values. So we're going to address our color space in a different way. Now this is really good for doing rainbows and things with, because we don't have to think about, well, what color value is yellow or Kermit green or whatever. We don't need to worry about that. We can just set the hue based on a value between 0 and 1. And we index the I again, so however many RGB LEDs we've got. So let's run this and see what happens. So this is going to set them all to a particular color. So if I set that hue to be 2, for example, so they started out a bit of a yellow color, so it's looking a bit more green. So if we do 3, I think that's pure green. Yep, if we go to 6, that's probably going to be another pure value, so that's going to be pure blue. And if we go all the way up to 1, that's going to be pure red, like so. And interestingly, 0 is also red, because it's a circle and you come right back on yourself. The saturation is 1, so if we put that down to half and click run, then we get half the value, half the saturation, which looks a bit of a like pinkish color. Let's make that half that again, so it's a quarter. Run this and see what that looks like. So it's getting much whiter in value, and the brightness is currently half. So let's set that to 1. It's going to get very bright in a second as I do this. Yeah, there we go. That's very, very bright. And if we put that saturation back up to half, we should see a lot more red come through. And it doesn't look too much on camera, but I can see that it's changed. Let's try it to 75. So 75%. Yeah, it's definitely getting red there. Let's make it 90%. So it's definitely red now. Look at that. Again, we can change that brightness. We can do like 0.1, so it's very, very, very dark. So it's barely lit up. You can just about see that there's some colour there, but it's really not very bright at all. So that's using hue, saturation, and brightness. We can adjust things, and we can do clever things with rainbows with that. So let's stop that. Let's go to our next one, which is test number 4. So this one is going to do another loop. We're going to set based on some fancy maths in here. Let's have a look what happens when we do this. So it's going to change colour. It's going to change colour depending on what the value of H and I are. So you can see there it's going through all the different colours, all the different hue values, and it's setting all the pixels to be the same colour as well. So let's stop that one, and then let's look at our test number 5, which I think is the last one. And what we do on this one, so we've got a direction in here, so we can see that what's going to happen. We've got the usual variables in there. Let's just go back up to the top. So number of LEDs, frames per second, and speed. We're setting up our plasma to the APA 102. We're going to start it with the frames per second. Not sure that we use offset in here. Yes, we do. We do use offset. We use direction, brightness, saturation, and saturation direction. So I'm going to run it and let's see what happens. And then we can have a look at what's going on there. So look at that. We've got this really nice sort of rainbow strobe type effect where it's chasing round. And I've got a little printout there so you can see that the hue values are increasing from 0 to 1. Tiny bit at a time. The brightness is also going up, and that's what's giving it that sort of pulse effect. You can see it's changing. And then the saturation is also changing as well. So, oh no, sorry, the saturation is the only thing that isn't changing. I was going to add that to the code, but it really didn't add anything extra to the animation. So you can see there what's going on. So let's try something on here. With this being quite an interesting one to look at, let's change the number of LEDs. Let's try 15 first of all and run this. So if I do this, it gets to there and it just stops. If I change that to 100, let's try that. And we can see there it's going to go round, but it doesn't get all the way round. There's still quite a bit of, yeah, stopping about there. There's still quite another bit of loop that it can go round. And let's try 120. Again, I'm not sure exactly how many LEDs are on this strip. Could probably work it out if you knew the pitch. Yep, that's still, it's more than 120. Let's try 130. Probably got around about 130. Let's try that. Oh, no, there's still more to go. Let's try 140. That must be nearly it then. Let's have a look. So, is it getting all of them? No, there's about 4 or 5 left on there. That's why 50 was a good enough guess. It was the right kind of order of magnitude. Now, these can be completely laid out. They don't have to be, you know, held within here. We can do whatever we like with them. It just looks quite a nice effect having them all in the little coil, I thought. So there we go, look at that. Looks really, really interesting. And they're in sort of a silicone container as well, so they are quite protected. And it also gives them a nice kind of glow. So I particularly like these really dense ones. I think they look amazing. One of the ideas I've got is creating a dog coat. I need to figure out, like, battery wise how I'm going to have like a heavy battery on my Chihuahuas, but I'm sure we've got some options. I was thinking maybe one of these little battery packs or something, but there might not be enough juice in one of these to power RGB LEDs for a long time, particularly when there's quite a lot of them like that. But yeah, I was thinking, like, you know, you could have a disco dog. You could have, like, for not this time of year, but when the light is going darker in the evenings, and we could have like the dogs light up different colours. And if I attached like a Bluetooth module to this, I could remotely control what colour the dogs or what pattern it is. And maybe, like, if we attached an accelerometer to this as well, when the dogs sort of do their business, it could be like arrows pointing. I don't know. All kinds of things that you could do with this. So there's a really cool project that I've been watching. So Geeky Faye Art, or Ali, she's created an absolutely amazing project. And what it is a necklace. And it's made up of LED, RGB LED strips. There's quite a few of them. And there's like a long one, smaller and smaller. So it's kind of like a V shape. And she's added that to a air quality sensor. So if somebody walks past her and they're vaping or they're smoking or there's like bad quality smoke in the air, it will sort of pulse a red colour from below. If she's in really good quality air, it's sort of a blue colour. So I would absolutely suggest you find that video and watch it. It's a really good YouTube make video as well. So yeah, really, really looking forward to seeing more projects and thinking about what else we can do with RGB LEDs. There is just so many things. You can cut these up, join them together with other wires and make matrices. You can make like a matrix display. Now I have got just behind me there it's driven by an Interstate 75. It's an RGB matrix, and there's, I think, 64 by 64 pixels. so a hell of a lot of pixels on there, and you can make it drive and make it display all kinds of things. Now the only problem I've got at the moment, if I'm live streaming and I'm streaming at 60 frames per second, it looks awful on there. It looks really, really bad, but I can probably film it using a different camera with a different setting to get a really good quality image grab of that. So I'll be covering that one off on a different video. I was going to look at that perhaps today, just because it's an extension of RGB LEDs, just having them all in a matrix already defined and ridiculously close together. Cool. So if you're watching this live, this is the point in the video. If you're watching this on replay, this is the point in the video where I'll say thanks for watching and I shall see you next time.